Welcome back to The Explainer. Today, we're jumping right into a fundamental conflict at the absolute heart of computer science. We're talking about a structural divide that has essentially dictated how software is built for nearly a century. And we'll look at how a radical new approach might just rewrite those rules. We are talking about the tape versus the tree. So let's get started. Okay, let's dive into this. What if the very architecture of modern software, the way your favorite apps, websites, and databases function right now, is built on an artificial, rigid boundary? If you've ever found yourself wondering why modern software can sometimes feel so bloated, slow, or just overly complex, well, we really have to question that original blueprint.
But to question that blueprint, we actually need to go backward in time. Before we can even look at the bleeding edge of database technology, we first have to revisit a theoretical machine invented way back in 1936. This is the machine that set the stage for literally everything that followed.
Which brings us to our first stop, Section 1, Turing's 1936 baseline machine. So, the brilliant English mathematician Alan Turing wanted to understand the absolute limits of computation. To do that, he stripped it down to its purest possible form. His theoretical machine basically just chugs along a track, scanning a symbol inside a square cell on a tape. It then checks a completely separate function table to figure out its next step. And finally, it takes action. It replaces the symbol, changes state, or moves left or right. That's it. Just 3 essential steps to perform any conceivable computation.
But here is the absolutely crucial takeaway from Turing's design. He established 2 completely separate essentials of computation. First, you've got the representation of information. These are the passive symbols just sitting quietly on a tape. And second, you have the recipe for computation, the active step-by-step instructions located over in the function table. The tape and the table are distinct, physically separate entities. It was an absolute genius move for 1936, but it set a very, very specific precedent.
And that physical separation laid the groundwork for our next topic, Section 2, separating nouns and verbs.
And this brilliantly illustrates the philosophy computer science basically just ran with. We started treating the tape as our data, our nouns, passive objects just sitting lazily waiting to be acted upon. And we treated the function table as our code, our verbs, the active, sweating instructions doing all the heavy lifting. Standard software architectures enforce a massive brick wall here. You have a database optimized for storing passive nouns and a completely separate application layer for executing active verbs.
But as software scaled up, this historical divide started causing some major headaches. Let's look at Section 3, the impedance mismatch problem.
This brings us to a pain point every single software developer knows intimately: object-relational impedance mismatch. Because we separate the database schema, the nouns, from the application logic, the verbs, we introduce incredible friction. It's like a French architect and a Japanese builder trying to construct a house together without speaking the same language. To get the code and data to talk across this boundary, developers have to build complex translation layers, massive driver libraries, and deal with heavy parsing overhead across network connections.
Now let's take a look at how the industry has tried to handle this translation problem. MongoDB, which is a NoSQL engine, keeps things decoupled. Storage sits over on a disk, while a separate client app holds the logic. Serverless platforms, like AWS Lambda, take that decoupling to the extreme. Compute is totally ephemeral, and state has to be fully offloaded. But then we have the Hierarchical Script-Database, or HSDB. It offers a radical alternative, homogeneous coupling, where both code and data reside together in a single, unified kernel. But before we break down exactly how HSDB pulls that off today, we need to look at an early attempt to fix this divide. Section 4, Early Trees, the MUMPS database.
Let's see how this evolution builds across our timeline. We started with Turing's tape in 1936, right? Then, amazingly, right in the middle in 1966, we had the MUMPS database, an early implementation of the tree. And this directly sets the historical precedent for the modern hierarchical script database that really emerged in the 2010s and 2020s.
MUMPS, which was developed at Massachusetts General Hospital, was absolutely decades ahead of its time. I mean, running on a modest PDP-7 computer in 1966, a machine with less memory than your smart toaster, it featured schema-free storage using a hierarchical data model. But its greatest innovation was tightly integrating a database directly with a programming language. You could literally store executable scripts within the tree nodes. It completely bypassed the NoSQL movement of the 2000s, 50 years early, just by keeping executable instructions and state data within the exact same tree structure.
And that brings us squarely into the modern era to explore the ultimate paradigm shift. Section 5, HSDD and Code Data Locality.
This quote from researcher Kyle MacLean-Smith perfectly captures the architecture of SeedTreeDB, which is a patented implementation of HSDB. He points out that if traditional systems separate nouns from verbs, HSDB places them next to each other in cohesive sentences and paragraphs. It is just a brilliant linguistic metaphor. By using JavaScript for both data retrieval and scripting, HSDB mathematically merges the application layer and the database layer into a single, cohesive unit.
So the crucial concept here is code data locality. By putting the nouns and verbs into the same sentences, you achieve total coupling. You keep the executable instructions and the data they manipulate physically close in memory. This entirely bypasses the need for complex translation layers. And for the end user, this translates to blindingly fast performance and incredibly efficient software, because the execution path and the data retrieval path become one and the same.
Let's look under the hood at the actual mechanics of this tree. It operates as a unified execution and persistence engine running in a single JavaScript kernel. Every node can contain both function properties, the verbs, and data properties, the nouns. And it's totally event-driven. When external events occur, the database acts as a living structure, dynamically self-modifying and sprouting new child nodes automatically. Instead of a static filing cabinet, it evaluates code as a non-halting, self-reproducing automaton. It's a living ecosystem.
And the mathematical underpinning that makes this living structure possible is called Pythagorean metal. Instead of relying on static, rigid state machines, HSDB uses infinite, deterministic, geometric sequences. By using specific mathematical formulas, it produces scale-symmetric patterns that act as unique coordinates for data structures. In simple terms, it fundamentally replaces the need for physical storage guarantees with continuous, bulletproof mathematics.
Which leads us to our final topic and the ultimate implications of replacing the tape with the tree. Section 6, Re-engineering the Universal Machine.
Now, what's really interesting here is the surprising twist. This purely logical merging actually alters the physical behavior of the computer itself. Because of code data locality, data doesn't have to travel as far across the system bus. This physically decreases power consumption and lowers memory bandwidth requirements, all while accelerating instruction execution. Because it undeniably improves how the computer hardware physically operates, it legally qualifies as a hardware-level technical improvement. That gives it strong Section 101 patent eligibility under U.S. law.
So, I'm going to leave you with this final provocative thought. Does the future of computing really lie in constantly patching together more complex translation layers just to bridge an artificial divide we inherited from 1936? Or does it lie in mathematically unifying the code and the data into a single living tree structure? It's a massive architectural shift to consider. Thank you so much for joining me today and for learning along with me on this explainer. See you next time.